All right, so in this video, we're going to create some examples of calculating statistics with grouped data. So sometimes it's important to be able to, you have maybe a histogram that you want to summarize, estimate some statistics for. Since we don't have the original data and the data has been binned, we can't get the exact value, but we can at least estimate it. And typically the way that we do this is with the midpoints. So in this case, we have some labels for our data. We're grouping data from 1 to 3 years, 4 to 6 years, 7 to 9 years, and 10 to 12 years for some set of students. And then we're also going to enter some frequencies for the number of counts that are in each of these bins. Now, if I create a bar plot of this, then my labels are listed here. My arguments are the names of my categories, and we can see the counts are being used as the bin heights. Now, if I want to calculate the estimate of my statistics, I need to calculate the midpoints. And typically the way the midpoints are calculated is that I use the midpoint of the lower bound to the upper bound, to the lower bound of the next group. Particularly in discrete values here. So my midpoint is actually 1 to 4, not 1 to 3. So that's actually a common error that some people will make with discrete values. So here I'm calculating my midpoints again, 1 to 4. So the midpoint of that divided by 2, 4 to 7, the midpoint of that, 7 to 10. And then the next group would be the next value after 12, which would be 13. And so I've calculated those here. And then the total would be the sum of my frequencies, because that's going to be the number of total people in my data set, the total number of observations. And now the weighted mean is going to be the frequency times so the number of counts times the midpoint values divided by the total. So essentially we're imagining that in this first category, my midpoint is 2.5 years, and I would calculate essentially there's 9 people that are in that bin. And so I'm going to treat them all as if they're at 2.5 years. And again, that'll give me my estimate. So frequency times the midpoint gives me, again, the weight for that bin, and then I'm going to divide by the total. And now if we print that to the screen, I get about 6.65. Now, just again, to run through what the calculations are doing. So my list of midpoints, again, those are the center parts of my bins, essentially. Calculating the frequencies times the midpoints are calculating these frequencies times each of these midpoint values. Again, essentially to get the sum of the values in the entire bin. Again, an estimate of them. And then when I calculate the sum of those, that'll be my numerator for my median, for my mean. And then when I divide that by the total, again, that's the sum of all of my observations, then I get my mean back. So that's what that formula is doing. Now, if I have actual discrete values that represent only one bin at a time, then I don't need to calculate my midpoints at all. And so in this case, I can create a bar graph of this data. So this was related to the number of hours of sleep that students were getting. And we can see that most of them are getting around 8 hours of sleep and falling off on either side. And so again, we can calculate here, we don't have to calculate the midpoints because these bins represent individual hours of sleep. And so we can go ahead and just calculate the sum of the frequency divided by the sum of the frequency times X times divided by the sum of the frequency. And we get about 8.45, and that makes sense. The biggest values are at 8, and there is a slight increase, so it's like right skew, in that the bins on 9 and 10 are bigger than the ones on 7 and 6. Now, if I want to calculate the standard deviation for, again, the sample standard deviation for a problem like this, I'm going to divide by n minus 1, so the sum of all the frequencies minus 1, and I'm going to calculate x minus the weighted mean, quantity squared, times the frequencies. But those weights still go in there, and if I run that, then my sample standard deviation will be this. Again, I'm taking the square root of the whole thing at the end. Now, if I am working with essentially a probability distribution, then I can't do the sum of the frequency minus 1. I can only do the population standard deviation. And so I can only divide by the sum of the frequencies. So my expected value is essentially my weighted average. And so here I just have two values for X. So maybe there's a raffle and you could win $500, but it costs you $1 to play. So there's a 1 chance in 1,000 that you will win the raffle, but then there's a 999 out of 1,000 chance that you will just pay the $1 and not win anything. So we can run and enter that into our memory. And then the frequencies, again, these are probabilities. And again, our formula for the expected value is the same as our weighted mean. We're going to multiply the frequencies by our x values and then divide by the sum of the frequencies. And what this means is that, again, what essentially you're going to do, they're going to take in $1,000 altogether and they're going to give half of it away. But basically, that means that the $1,000 that everybody paid in is not coming back. Only half of it is coming back. So if you play the raffle, then your expected value, if you were to do this a whole bunch of times, would still be that you would ultimately lose money. You would lose half of your raffle price. If we want to calculate the standard deviation of this probability distribution, however, we can't do the sum of the frequencies minus 1 as we saw before, because what's going to happen is sum of the frequencies is 1. And so if we subtract 1, we divide by 0. So we can only calculate essentially the population standard deviation. But again, we have probabilities. And this, you would think if you're looking at all 1,000 raffle tickets, that is a population standard deviation. And then finally, we have one more example here involving several probabilities. This particular example we could think of as the number of people that call out sick on a particular weekend at a restaurant. So there's 4 employees, and most of the time, 60% of the time, nobody calls out sick. 20% of the time, 1 person calls out sick, and so on until you get down to 4 people calling out sick. So these are our X values, the number of people that call out sick, and these are the probabilities. These should add up to 1. And then our expected value, again, is going to be the frequencies times the observations divided by the sum of the frequencies. So again, fewer than 1 people on average call out sick, which is what we'd expect from more than 50% not having any absences. And then again, the standard deviation that we're going to have to calculate here, X minus our expected value squared, add them all up, multiply by the frequency, and then take the square root. You do have to watch your parentheses. And when you calculate that, you get this as your standard deviation.